Uranus has a 22-year-long winter. On a planet like that, if it was habitable, everything would be frozen and covered in ice, white and gray desert all around. People would have to stock up on food and supplies, make extra sturdy buildings and homes, and always wear thick, warm clothes. Finally, transportation would be next to impossible. But thanks to the Sun, each planet in our solar system has unique weather, climate, and seasons. There are several reasons contributing to that. First of all, it's all about how far a planet is from the Sun. If a planet is close, like our neighbor Mercury, it gets a severe sunbath. But if it's far away, like the dwarf planet Pluto, it gets frigid even during summer. Now, think about how fast a planet spins. Planets that take their sweet time to rotate, like Mercury, have super long days and nights. That means one side gets toasty hot when the sun's out and freezing cold when it's dark. Earth is pretty balanced with its moderate spin speed. The atmosphere matters too. A thick atmosphere keeps temperatures from going wild, but if there's almost no atmosphere, things heat up and cool down immensely. The tilt of a planet's axis and the orbit shape are crucial as well. Even on Earth, places near the poles get 6 months of daylight and 6 months of night. And if a planet's path around the Sun is like an oval, it heats up and cools down more than it moves. Now, no two planets are unique. While some have these changes, others don't. Let's start with Mars, our favorite little planet and potentially our future home. It's the fourth wheel in our solar system and has a quirky way of doing seasons. Like Earth, it has 4 of them, although they're roughly twice as long as those on Earth. But this planet has an eccentric egg-shaped orbit. Because of this, its orbital speed varies more. This influences these seasons. Martian winters last about 4 Earth months. They're also much colder than on Earth. Near the poles in winter, temperatures can get down to minus 190 degrees Fahrenheit. One hemisphere grows an ice cap as winter rolls in, snatching about a quarter of the atmosphere as dry ice. Then, in spring, it gives it back. Mars also doesn't have the luxury of massive oceans like Earth to balance out its extreme temperatures. Scientists believe it might have had some of that in its early days, but now all the water is gone. With no water, Mars can hit very low temperatures in winter and hotter summer days. The grand gas giant Saturn has a slightly more tilted axis than Earth. However, despite its elliptical path and tilt, it stays consistently chilly. That's because it's way out there, far from the Sun's warmth. Even though it's summer, Saturn remains distant and doesn't get too cozy. It also has a thick atmosphere. The atmosphere on a planet acts like a temperature regulator. If some part gets too hot or cold, the atmosphere gently distributes this temperature across the planet. So, while one side might catch more sunlight during its equinox, the thick air ensures things stay relatively cool. Up high in Saturn's atmosphere, though, it's a different story. Temperatures can swing from seriously chilly in summer to an almost absurd minus 312 degrees Fahrenheit in winter. Uranus is the next planet, the ice giant. With an elliptical orbit and a serious distance from the Sun, it's stuck in a perpetual deep freeze. Its thick atmosphere also keeps temperatures frosty throughout the year. Uranus has a wild tilt, 3 times bigger than Earth's. It's almost lying on its side, and is probably one of the most intense places in our solar system. During Uranus's summer, one pole gets full sun, while the other end faces the deep chill of darkness. In fact, because of its weird tilt and rotation, Uranus is even colder than its more distant neighbor Neptune. As we mentioned, each season on Uranus lasts around 22 Earth years. That's as close as we get to George Martin's fantasy books. That's because Uranus takes a leisurely 84 years to complete one path around the Sun, so its journey through the year is very slow. The final planet in our solar system is Neptune. It's the most far-away icy giant. It has a tilt almost the same as Earth's and a nearly circular orbit, so it feels like it's supposed to be a bit more balanced. However, this planet maintains a bone-chilling atmosphere with unimaginably low temperatures. That's because Neptune receives only a tiny 0.1% of the sunlight Earth enjoys. On Earth, there's a gradual temperature shift from near to far. On Neptune, because of its circular orbit, there's only one atmosphere taking a spotlight. Unlike its neighbor Uranus, Neptune gets a bit of warmth from its core. But this warmth doesn't help much. The cold is pretty consistent, whether it's winter or summer. But some planets don't bother with traditional seasons. They just imitate them by having different temperature cycles throughout the year. These planets include Mercury, Venus, Mars, and Jupiter. Mercury is the closest planet to the Sun. Mercury is very weird, because one full day-night cycle on that planet equals 176 Earth days. After half a year on Earth, it's finally time for Mercury people to go back home from work. That's because it moves in an egg path. This is also the reason why it has some wild temperature changes. Sometimes it's very close to the Sun, sometimes it's not. At the same time, it has no atmosphere and no protection from the Sun. This results in extremely hot days and extremely cold nights. But that means it has plenty of time to go from scorching hot to freezing cold. When it's farthest, that's Mercury's true winter, or at least how we call it. So if it had seasons, there would only be two. The next planet is Venus. It's a planet of relentless heat. Forget about seasons. It's just plain hot there all the time. It's super close to the Sun, and its almost circular orbit and tiny tilt of 3 degrees mean temperatures stay pretty steady throughout the year. Even in the supposed winter or the middle of the night, the temperature doesn't dip below 820 degrees Fahrenheit. It also decided to have a weird spin. Venus spins in the same direction as it moves around the Sun. That means the Sun is always right overhead, pouring its entire fiery love on the planet's surface. Venus doesn't really do the seasons like Earth. The closest they have to seasons is 225 days with at least 4 hours of sunlight. This you could call Venus's version of spring and fall. Jupiter, the big guy in our solar system, doesn't bother with the whole seasons drama. It keeps things simple with a tiny tilt of 3 degrees, almost as laid back as Mercury. Plus, its orbit is a close match to a perfect circle, so it doesn't have much variation in sunlight. Also, with a speedy rotation of less than 10 Earth hours, there's no time for the appearance of seasons from long nights. Winter on Jupiter is basically a repeat of any other time of the year. And finally, Pluto, which is still not a planet, but still worth looking at. Pluto resides on the outskirts of our solar system. This little outcast is the definition of cold. The temperatures are around minus 380 degrees Fahrenheit. It has the weirdest orbit, too. Its orbit is very long, elliptical, and tilted. Pluto travels a huge distance from the Sun. That, together with an almost non-existent atmosphere, keeps Pluto in a perpetual cold state. Winters there can get a bit more extreme than average. However, the biggest shift someone stranded on Pluto would notice isn't the temperature, but the Sun's brightness. Always thousands of times fainter than our earthly view.
I hope you feel well rested, because I've got a tough task for you. Don't worry, it's fun. You're going to visit different planets of our solar system and try to run on each of them. Let's figure out where you can run the fastest and where you can barely walk. The fastest man on Earth, Usain Bolt, can run with an average speed of about 23 miles per hour. But his top speed is higher, up to 27 miles per hour. Sadly, we can't all be Usain Bolts. The average person runs at a speed of 6 to 8 miles per hour. But maybe there's a planet out there where you can beat the famous Jamaican sprinters' records. But first things first, what will affect your speed when you run on other planets? For one thing, gravity. Depending on how strong it is on the planet you visit, it'll influence your weight. And in most cases, the heavier you are, the more slowly you run. Plus, on all other planets in our solar system except Earth, you'll have to wear a bulky spacesuit. Without it, your chances of survival there are non-existent. And don't forget about extreme weather conditions on most planets. It's either freezing cold or boiling hot, or very, and I mean it, windy. Anyway, your amazing journey is about to begin. Buckle your seatbelt. The first planet on your itinerary is Mercury. As you sneak a peek at this world through the window of your spaceship, you notice that the planet looks eerily similar to the good old moon. But just a few moments later, you realize it's just an illusion. All over the surface of Mercury, you see craters left by space rocks. This may make your task of running on this planet way harder. This and your bulky spacesuit. Duh. But you wouldn't survive on Mercury without this protection. The temperatures on the planet are extreme. 800 degrees Fahrenheit during the day and negative 290 degrees Fahrenheit at night. But there's one thing that can work in your favor on this unfriendly planet. Let's say you weigh 155 pounds on Earth. Then on Mercury, you'd weigh around 58 pounds, which means that despite your bulky spacesuit, you can move way faster than you do on Earth. And maybe your speed will even reach 13 miles per hour if you try really hard. The next planet on your itinerary is Venus, also called the Morning Star. While coming closer, you see a world very different from the bluish planet you might have seen in books. Before landing, you have to get through a super dense atmosphere made up of carbon dioxide. And while your spacecraft is descending, you're watching thick clouds of sulfuric acid pass by. Venus is often called Earth's twin because these two planets are of similar size and density. No wonder that on Venus, you weigh almost as much as you do on Earth, 140 pounds. So your weight is a bit smaller here, but don't forget about your spacesuit. And still, because of almost the same conditions on the two planets, you'd be able to run a bit faster than on Earth, at around 8.5 miles per hour. Your first impression of Mars is that it's freezing cold. The average temperature here is about negative 80 degrees Fahrenheit. Even from afar, the planet looks reddish. Once you make your first step on the Martian surface, you understand why. The ground's covered with rusty-colored dust. The same fine dust is floating in the air around you. Wherever you look, you see golden, brown, tan, and even greenish hues. They depend on the minerals that make up the soil. The size of the dust layer varies from area to area, but in most places, it's around 7 feet thick. That can make running much more difficult. On Mars, your weight would be much smaller than on Earth, a mere 58 pounds. This will help you achieve an impressive speed of 12 miles per hour. Aren't you a champ? What's that on the horizon? It looks like a tornado. Is it a dust storm? Then it's time to make a run for it. Dust storms sometimes cover the entire planet, and you can even see the largest ones from Earth. And now you're facing a problem. You see, Jupiter, as well as Saturn, is a gas giant. This means that the largest planet in the solar system, and Jupiter is so large it could swallow 1,300 Earths, doesn't have any solid surface. Well, you'll just have to imagine what your running workout would look like if you could run on Jupiter. This planet has an atmosphere that consists of hydrogen and helium gas. During your descent, you admire thick brown, yellow, red, and white clouds. They make the planet look colorful and beautifully striped. On Jupiter, you'd weigh 390 pounds. You'd have to break a sweat to simply walk there, wearing your clumsy spacesuit. If you could step on the planet's surface, that is. If you tried to run there, your best result would probably be a speed of 1 or 2 miles per hour. To make matters worse, it's extremely windy on Jupiter, with the wind speeds ranging from 200 to 400 miles per hour. Do you see those rings? That's Saturn, another gas giant with no solid surface. This planet's made up of mostly hydrogen and helium, and its temperature and density change the deeper you go. If you decided to leave your spacecraft and step on Saturn's surface, you'd just fall into the planet. But from above, it looks as if Saturn does have a surface. The seemingly solid yellowish-brown sphere is surrounded by several layers of clouds. The visible outer layer is made up of ammonia clouds. Under them, there are hydrosulfide clouds, and the innermost layer is made up of clouds of water. Even though Saturn is a gas giant, your weight wouldn't be very different here, around 165 pounds. That's because the planet's gravity is similar to that of Earth. But because of the conditions on the planet, and your bulky spacesuit, you'd run a bit more slowly there, at a speed of about 4 miles per hour. Before leaving, you admire Saturn's most famous feature, awesome gray, beige, and tan rings. These groups of tiny ringlets are made of chunks of rock and ice. You also spot several of the 53 moons of Saturn. Oh, that's Titan, an icy world bigger than our moon and even Mercury. It's the second largest moon in the solar system. The next planet on your way is a blue-green ball of ice and gas. That's ice giant Uranus. It has this beautiful hue because the light from the sun gets reflected off the planet's surface. Uranus isn't solid. Hit the brakes! If your spacecraft doesn't manage to stop in time, it'll fly through the upper atmosphere and sink into the icy liquid center of the planet. I doubt you'll be able to conduct your running experiment here. So let's just imagine what it'd look like. On Uranus, your weight would be around 138 pounds, and against all odds, you could actually reach a good speed here, at least 8 miles per hour. If you didn't get caught in a hurricane, of course. Extreme storms occur on the planet in the summer when Uranus is heated the most. Then, hurricanes can spread for more than 6,000 miles. The furthest planet from the Sun, Neptune, is 4 times the size of Earth, but 17 times as heavy. The blue surface you see when approaching Neptune is actually a layer of swirling gas and permanent clouds. The planet's mantle is made up of water, ammonia, and methane ices. It's the closest thing Neptune has to a surface. And still, there isn't solid ground for you to walk on. So, once again, try to use your imagination. On Neptune, you'd weigh a bit more than you do on Earth, 174 pounds, but your running speed would be just a bit lower than on Earth, around 5 miles per hour. That's the end of your active adventure. Which planet did you like running on the most?
Okay, picture this. In the not-too-distant future, you're heading out on a space vacation, and you need to decide which items are worth bringing along. But instead of checking the weather forecast, you open a gravity simulator. That's because you need to know how each object will behave on different planets. For instance, should you take this metal shovel with you or not? Well, according to your itinerary, it's going to be a long trip. You're planning to visit every planet in the solar system and even a few moons. But due to the difference in gravity on these space bodies, you're not sure how useful some of the objects you're going to bring along will be. Well, let's start with the basics. Tupperware. I don't know about other space travelers, but us Earthlings carry our Tupperware around everywhere we go. And still, if you were to transport it to, let's say, Mercury, it would most likely fly away into the atmosphere. These plastic containers you use to keep your food are too light. And since the gravity on Mercury is 2.5 times weaker as gravity on Earth, well, maybe you'll have to fill your plastic containers up before taking them out of your spaceship to have a picnic. If a Tupperware container weighs about 0.5 pound on Earth, it'll weigh just 1/4 of that on Mercury. Now, if we add some bananas, a handful of baby carrots, and 2 watermelons, then it'll be safe to carry it out of your space vehicle. You'll just have some difficulty making it all fit in a standard-sized container. But wait! Before you do that, you should know that the atmospheric temperature on Mercury can reach up to 800 degrees Fahrenheit. This means that any plastic container will instantly melt as soon as it gets in contact with the air. It'll burn up all the food, too. You can probably try taking a titanium container, that'll work, or just stick to astronaut food. Now, shall we say Venus? Okay, Venus. If you were to take the same empty container to Venus, it would behave similarly to how it does on Earth. This is because Venus is also known as our planet's twin. These two have much in common. For example, almost the same size and mass. And when the topic is gravity, the formula goes like this. The bigger the mass and the greater the density, the stronger the gravity. Venus's gravity is approximately 10% weaker than Earth's. So, yes, you may leave your spaceship with your container, empty or full, and enjoy a beautiful and scenic lunch on the surface of Venus. Now, you'll have to figure out a way to eat without taking your spacesuit off, though. The atmosphere of Venus is filled with sulfuric acid, which can irritate your nose and throat and cause difficulties in breathing. Or worse. Much worse. Now, you'll have to forget about taking anything too light outside on Phobos. A little hint for you, it's not a Greek island, not even Greek yogurt, although it's a cool name. It's actually one of Mars's moons. Here, even your spacecraft would need a little extra help to keep close to the ground. If it weighed as much as a school bus, any regular-sized person could pick it up with just one hand. This is because on Phobos, the inhabitants of Earth barely feel the weight of gravity. And be very careful when jumping around because one leap and you may fly straight into outer space.
Passengers on board the Voyager spaceship, please keep your arms and legs inside the vehicle at all times.
Well, you're approaching Jupiter, a gas giant. A never-ending storm is raging in its atmosphere. Plus, there's no solid surface there, which means no landing for you on this planet. If you look out the window, it might seem that you are moving through a giant cloud. But for the purpose of your experiment, it'll work just fine. Try throwing into the air that baseball you brought along in case you get bored of all the space travel. And measure the time it'll take the ball to hit the surface. If on Earth, the ball will fall at a speed of 32,174 feet per second. On Jupiter, the same ball will hit the ground at a speed 2.5 times greater than that. That's because Jupiter is more than 10 times as large as Earth and around 300 times as heavy as our blue planet. Now, if you move your spaceship just a little bit to the side, to one of Jupiter's moons, Europa, the situation will be completely different. Throwing a baseball in the air on Europa will mean never seeing it again. Gravity there is almost non-existent, which means that not only a baseball, but even a grown-up person can fly away any second. Now, on the other hand, if you decided to venture out of the spacecraft to explore Europa's gravitational field, why not try to lift the space vehicle itself? On Europa, a regular Earthling can easily lift up to 1,000 pounds, which is the equivalent of a full-size male moose. Or you can lift a pyramid-like formation of 9 regular people. The choice is yours. When approaching Saturn, be careful. While from afar, Saturn's rings look smooth and solid. From up close, you'll notice that they're made of chunks of ice and rocks floating in space. You won't want to have your spacecraft anywhere near those. There's also no solid surface on Saturn, which makes landing impossible. And the atmosphere is full of ammonia. Keep in mind that it's a pretty inhospitable environment for a human. Now, inside the spaceship, you find a collection of sci-fi books, enough to fill an entire bookshelf. Altogether, they must weigh around 400 pounds. Yep, that many books. And like someone with a superpower, you try to lift over 200 pounds of weight at a time. But guess what? You fail, because Saturn's gravity is too similar to that on Earth. Now, in case you got confused with all this gravity talk, when we're measuring gravity, we're speaking about the power of the force by which a planet or other space body pulls objects toward its center. So, if you need some help in organizing that sci-fi collection in alphabetical order, ask the crew to move the spaceship to a neighboring space body with a weaker gravitational pull, like Pluto. These days, it's not considered a planet anymore, just a dwarf planet and one of the furthest from the Sun's space bodies. You'll need an extra warm spacesuit to wear there. Pluto is freezing cold and has a tiny surface. It's smaller than Earth's moon. But it's a great place to test your strength. If on Earth it's kind of impossible for a regular person to lift an elephant, on Pluto you'll be able to pick up a baby elephant weighing around 265 pounds. Or even a medium-sized elephant that can be as heavy as 2,000 pounds. On your way back to Earth, you make a pit stop on Uranus. The coldest planet in our solar system has an average temperature of around minus 350 degrees Fahrenheit. So, if you attempt to get out of the spacecraft, you'll freeze mid-movement. Although gravity on Uranus is pretty similar to that on Earth, there's one thing that's very different: time. A 2-week getaway on Earth turns into a 3-year-long vacation on Uranus. Now, when you get sick of cold planets, you can travel back to warmer ones. Okay, now, Mars is definitely warmer than Uranus, but its average temperature is still about minus 81 degrees. On Earth, we only have such low temperatures at the South Pole during the winter. When you land on Mars, you'll start to feel light and strong at the same time. Mars's gravity is about 2.5 times weaker than that on Earth. So, in other words, you'll probably manage to lift your own body weight without any difficulty. So, all those handstands you've been dreaming of doing, you've found a place to fulfill your dream. The protective shield of our planet decays and eventually fails. So do our satellites. First, communication satellites in the highest orbits go down. Next, astronauts in low Earth orbit can no longer contact their mission control center. And finally, hazardous, relentless cosmic rays start bombarding everything on Earth, causing havoc and devastation. Are these the terrifying consequences of the planet's magnetic field reversal we're going to face? Right now, as you're watching this video, Earth's north magnetic pole is extremely out of whack. It's so serious that scientists will have to update the global magnetic field model released a mere 4 years ago. Does it all mean that the magnetic pole of our planet will flip soon? Well, be patient, we'll figure it out a bit later. You see, the magnetic pole is moving quite erratically from the Canadian Arctic towards Siberia, and these movements are very unpredictable. But it's normal for the pole to be moving. There are long-term records from London and Paris that prove that the North Magnetic Pole moves randomly around the rotational North Pole over periods of several hundred years. But the most astonishing thing about its movement is that it's speeding up. Around the mid-1990s, the magnetic pole unexpectedly accelerated from a bit over 9 miles to 34 miles a year. And recently, the pole crossed the international date line, moving toward the eastern hemisphere. The European Space Agency launched extremely accurate magnetic field satellites in 2013. Thanks to them, researchers have superb data they can use not only to make magnetic field maps, but also to update them every 6 to 12 months. That's how they were able to notice that the core field was weakening too. It might be a sign that the planet's magnetic field is about to flip. To understand this process better, we need to figure out how the core field works. Let's say we've got a bar magnet that runs through the center of our planet and has a north and a south pole. This magnet is incredibly strong, representing about 75% of the intensity of our planet's magnetic field at the surface. Our bar magnet is not only moving, but is also getting weaker, by about 7% every century. Admittedly, this bar isn't the perfect representation of the core field. It's more like electric currents generating Earth's magnetic field. Still, this model makes it easier to see what's happening to our planet now. The magnetic field of our planet plays an important role in protecting us from dangerous radiation and geomagnetic activity, which is the product of the interaction between the solar wind and Earth's magnetosphere. Earth's magnetic field also moves. Scientists have been studying and tracking the movement of the magnetic poles for hundreds of years. The historical motions of these poles indicates changes in the global geometry of the magnetic field of our planet, and they may point to the beginning of the field reversal too. That's what the flip between the north and south magnetic poles is sometimes called. You see, if the north magnetic pole moves a bit, it isn't a big deal. But a complete reversal might have a serious impact on the climate of our planet, as well as modern technology. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. So those scary events from the beginning of the video aren't likely to happen to us. The magnetosphere will continue protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current is negative charges called electrons moving through the metal. The current is what generates a magnetic field. Earth has a liquid iron core. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving through the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic radiation, which otherwise would be extremely dangerous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons and capable of reflecting radio waves. The interaction between these two layers and the magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. But sometimes, the sun starts shedding gargantuan magnetized clouds of gas that can accelerate to incredible speeds. They're called coronal mass ejections, or CMEs. They're ejected from the sun over the course of several hours. CMEs usually look like giant twisted ropes and can occur spontaneously. Their frequency varies according to the 11-year-long solar cycle. For example, at a solar minimum, you can observe one ejection per day, and when the sun is in its most active phase, there might be 3 CMAs per day. Coronal mass ejections disrupt the calm flow of the solar wind and cause serious disturbances that can damage stuff both in space near Earth, like satellites, and on the planet's surface. If coronal mass ejections make it to Earth, their interaction with the magnetosphere generates geomagnetic storms. Those can trigger auroras, happening when a stream of energized particles hits the atmosphere and lights up. And then there are also solar flares. They develop more rapidly and with much more energy than coronal mass ejections. Solar flares often occur soon after coronal mass ejections. The most powerful volcanic eruptions pale in comparison to solar flares that release 10 million times more energy. Within a few minutes, one solar flare can give out billions of tons of charged particles. Solar flares are also insanely hot, with temperatures reaching several million degrees Fahrenheit. Astronomers believe that such bursts of solar radiation happen when the sun's magnetic field gets twisted in some regions. At one moment, all the pent-up energy is released. The star sends out light and particles, mostly electrons and protons. Most solar flares last for minutes, but some continue for hours. A powerful solar storm can potentially cause a devastating global blackout on Earth. If not for the Earth's magnetosphere, the effects of the sun's activity would be much more devastating. Luckily, the magnetosphere deflects most of the solar material hurtling towards our planet from our star at a speed of over 1 million miles per hour. But even so, during space weather events, there's a lot of hazardous radiation near Earth. It can potentially harm astronauts and spacecraft. Plus, space weather can damage large conducting systems, for example, pipelines and power grids, by overloading currents running inside them. Scientists regularly map and track the overall orientation and shape of our planet's magnetic field. To do it, they use local measurements of the field's orientation and magnitude. That's why they've been able to conclude that the location of the North Magnetic Pole has moved by almost 600 miles since the first measurements were taken in 1831. The magnetic field of our planet reverses on a timescale varying between 100,000 to 1 million years. One can tell how often it happens by looking at volcanic rocks at the bottom of the ocean. They capture the orientation and strength of Earth's magnetic field at the time of their creation. So, dating those rocks gives us a good picture of how our planet's magnetic field has evolved over time. From a geological point of view, field reversals happen quite fast, but they are extremely slow from a human perspective. A complete reversal normally takes a couple of thousand years, but during this time, the orientation of the magnetosphere may shift, exposing more of Earth to cosmic radiation. Such events tend to change the concentration of ozone in the atmosphere. In any case, scientists can't say for sure when the next field reversal will happen, but they keep mapping and tracking the movement of our planet's magnetic north. By the way, the Earth isn't the only planet with a magnetic field. Gas giants, like Jupiter, also have a conducting metallic hydrogen layer that generates their magnetic fields. Jupiter's internal magnetic field prevents the solar wind from interacting directly with the planet's atmosphere. Bang! Another hit on Jupiter. Let's see. Gas giant, the largest planet in the solar system, 318 times bigger than the Earth, 2.5 times bigger than the rest of the planets in the solar system put together. One more interesting thing. If it got any bigger, it would actually become smaller. You see, with more mass, the planet would be denser. That would cause Jupiter to start pulling in on itself. Scientists say Jupiter could have 4 times greater mass, but still keep the same size. It takes 10 hours to make a full rotation on its axis. It's the fastest spinning planet in our solar system and gets hit by so many space objects all the time. This was discovered by amateur astronomers observing Jupiter and saw some unusual flash at the planet's surface. Impact events cause flashes like that, and for some reason, Jupiter gets more impacts than other planets. In 1994, astronomers discovered Shoemaker-Levy 9, a comet that broke apart and collided with the gas giant. The original comet was approximately the size of one that erased the dinosaurs. However, this asteroid fell apart into more than 20 fragments. They darkened the planet's surface, and it remained like that for months. 15 years later, in 2009, astronomers saw a black spot on Jupiter, the size of Earth. It was the result of an asteroid around 650 to 1,650 feet in length. The biggest asteroid recorded on Earth hit the area of Tunguska, Russia in 1908. This caused a massive explosion, even though no one ever found a crater. So, why is Jupiter the target for so many space objects? Asteroids and comets that pass by Earth and Jupiter go almost at the same speed. The number density of the space object that may interact is almost the same too. But the cross-section of what they might hit is very different. Jupiter has 11 times the diameter of our planet, which means it has around 125 times the cross-section. The more massive some planet is, the stronger its gravitational attraction. So, it will entice some space objects drifting by. Our gravitational field is weaker than Jupiter's. If some object passes near us moving at a speed of 22,300 miles per hour or less, our gravitation will attract it. Asteroids and comets usually move at bigger speeds. Jupiter attracts most of the comets and asteroids passing by. If our planet was hit by such big objects as frequently as Jupiter, we'd have extinction like with dinosaurs thousands of times more often. In 2020, scientists found there was an unusual asteroid in the orbit of Venus, the first one there. The size of a small mountain and rich in minerals we can find in Earth's deep rocks. They even think it could be a clue to a bigger set of asteroids created when our solar system was forming. That's not the only mystery around Venus. The planet has insanely violent winds that drive clouds and storms around the planet at speeds greater than 220 miles per hour. That's 60 times faster than Venus itself rotates. Also, scientists are still not sure what happened with its oceans. They believe since the planet is so close to the sun, the water evaporated and went into the atmosphere as steam. It trapped heat coming from the sun, heat that would have vaporized more and more water over time. Venus probably had an environment like on Earth, but a very long time ago. The theory says many comets and asteroids were slamming into Venus. Billions of the planet's pieces were flying all around. Some may have even crashed into Earth's moon. Pieces that slammed into our planet are probably buried very deep, since we have greater geological activity than the moon. Uranus also had a collision, but a more serious one than asteroids. The rest of the planets in our solar system mostly have an axis of rotation that kind of points up from the elliptical plane. Uranus is tilted, lying on the side, so a season there lasts 42 years, when either its south or the North Pole is pointed at the sun. Most of the planets also rotate counterclockwise when you see them from above our solar system. Venus does the opposite, which means maybe it was kicked off axis a long time ago. Uranus may have collided with the other space body millions of years ago. When our solar system was still very young, the orbital configuration of Saturn and Jupiter may have crossed. Their gravitational forces kind of created orbital momentum and transferred it to Uranus. That knocked it off axis. Millions of asteroids orbit the Sun, and not so many pass by Earth from time to time, so we don't have some dangerous space bodies coming toward us. The plan is to visit Mars in the 2030s, and scientists hope Mars won't be a target of some bigger space bodies. New craters are formed on the red planet every 1 to 2 days. They can be 13 feet across, which means they could have been formed by objects that are the size of a soccer ball. Since the atmosphere there is thinner than ours, smaller bodies can enter easier. Most of the Martian north is smooth lowlands. The south is higher, full of craters, and the planet's interior has a surprising amount of rare metals. The theory says this is because a big celestial body collided with Mars and tore away a part of its northern half. Debris from that asteroid circled the planet and then mixed into two small moons that orbit Mars. We also have some Mars rocks on Earth, found in the Sahara Desert, Antarctica, and some other places across the globe. Some of these rocks have gas that's chemically the same as the atmosphere on Mars. Rocks probably came due to a big explosion that happened when some larger asteroid or meteor that was ejected from Mars and landed on our planet. Mercury also has a thin atmosphere, so there are many smaller strikes there. Imagine waking up, going to your window, and see there are micrometeor showers every morning, which is something that happens on Mercury. This strange weather pattern shapes its atmosphere, called an exosphere. Mercury is so dense, its heavy iron core accounts for 2/3 of its total mass. Scientists think it could have been bigger in the past, but many collisions got the surface sort of scraped off. It's been constantly bombarded by rocks from space that left marks with craters. Plains on its surface seem to have been created because of volcanic lava spilling over the surface and then dried smooth. Many craters are filled with such a material, which means there's one more thing that rocked Mercury's world: volcanoes. There's an unusual group of asteroids discovered near Neptune. Wide range in sizes, from big metropolitan areas to tiny pebbles. They are thought to come from an asteroid group called the Kuiper Belt. It makes a ring well beyond Neptune. But these new asteroids have different colors than the Kuiper Belt. They're so far away from the Sun, their surface was supposed to stay almost pristine, but they have a similar color to those sun-baked asteroids around Jupiter. Like the rest of the planets, Neptune gets heat from the Sun. But there's something mysterious inside the planet that makes it generate more heat than it gets. This affects its weather, and Neptune has the weirdest weather in the whole solar system. Massive storms, insanely high winds, cirrus-like clouds that rapidly change all the time. There are dark spots in its atmosphere. They come and go. We receive 1,000 times more sunlight than Neptune. Gas giants like Saturn and Jupiter can protect our planet from asteroids. Without them, the big impacts that created enough debris to form both moons and other planets would happen more often. There's a huge asteroid going around Saturn, which could be a potential flyby by 2031, more than 10 times bigger than the asteroid that erased the dinosaurs. Titan, one of the moons orbiting Saturn, 80% more massive than our moon, is actually the only moon in our solar system that has an atmosphere. It's 1.5 times thicker than ours and consists mainly of nitrogen, like our atmosphere. No one knows where all that nitrogen came from. However, unlike Saturn and most of the other places in our solar system, its moon has a real potential to host life.
Have you ever wondered what it would be like if every planet in our solar system was the size of Earth? Well, it's time to dive into this mind-boggling scenario. Let's imagine what each planet would look like if they were as big as our beloved blue planet. Would the barren red landscape of Mars suddenly become a lush green oasis? Would the massive swirling gas giant Jupiter just disappear? And how would it affect our solar system as a whole? Are we all doomed? Buckle up and let's find out. The first planet on our list is Mercury, the smallest planet in our solar system. But now, forget about the moon-like Mercury. Instead, picture yourself on the surface of a super dynamic incandescent inferno. There are a lot of craters and active volcanoes around you, and right in front of you is a huge, blinding bright sun. What a nightmare! But let's break these changes down. Well, along with the size of Mercury, both its mass and gravity would increase. In that case, it's possible that Mercury would have more atmosphere. Temperatures on Mercury are extreme, not only because it's very close to the Sun, but also because of its very thin atmosphere. So during the day, the temperatures there reach 800 degrees Fahrenheit. And at night, it becomes terrifyingly cold, down to -290 degrees Fahrenheit. But now, when the gravity is stronger, Mercury could have a denser atmosphere, so the heat would be better distributed across the planet. And the atmosphere isn't the only thing that could make it hotter. If Mercury became bigger, it would likely experience increased internal heating due to gravitational compression. And hypothetically, its tectonic activity could increase. In other words, more interesting landscape, more mountains, and more scary active volcanoes. Congratulations, you've turned Mercury into Venus 2.0. For us, all these changes wouldn't be very pleasant. Now it would become much harder to send our spacecraft there, so it's better for Mercury to stay as it is, small, calm, and boring. Basically, the complete opposite of our next planet, Venus. So what would happen to Venus if it was Earth-sized? Actually, nothing. It wouldn't change at all because Venus is already almost the size of Earth. It's even called the Earth's twin, although twin is a big word, of course. In reality, we couldn't be more different. Venus is often called the morning star because it's so bright and visible in the sky. But don't let its beauty fool you. This planet is one of the most inhospitable places in our solar system. Its surface is hotter than a freshly baked pizza, around 900 degrees Fahrenheit, and it's covered in thick clouds of sulfuric acid that would dissolve any human who tried to visit. So, unfortunately, you won't be planning any trips there anytime soon. So let's move on to a planet that, unlike Venus, could potentially become a new home for us, Mars. Picture yourself standing on Mars's surface, watching the blue sunset and breathing in a refreshing breeze of air. Yes, you read that right, air. Moreover, you could be surrounded by plants, animals, and basically feel like you're on Earth. But how is that possible? Bigger Mars would have a stronger magnetic field and gravity. This would lead to a richer and denser atmosphere. It would likely have a wider range of gases, including oxygen. Wouldn't that be cool? Also, a denser atmosphere could distribute heat across the planet, so Mars would become much warmer and cozier. And here comes the most important change: liquid water. Mars actually has some frozen water at its poles and in subsurface reservoirs. But with a stronger gravitational pull, it could potentially stabilize liquid water on its surface. Hooray! However, it's not all fun and games. New Mars would also have a volcanic personality. It's already geologically active, but now its internal heat and pressure would skyrocket. That means more frequent and more crazy volcanic eruptions. Imagine how exciting it would be to witness such eruptions on another planet, if you manage to escape the consequences. In general, the planet could become greener and lusher, but not safer, although it would still be great to see it. But it's time to move on to the giants of our solar system. And if we're enlarging the planets before, now it's time to squeeze them really, really hard. If Jupiter became 11 times smaller, oh boy, what a disaster that would be. The first thing we'd notice is a change in gravity. And I say we'd notice because now we'd have no choice but to move somewhere. Jupiter experiences from 30 to 100 collisions with large asteroids per year. No big deal, all because of its strongest gravity, which attracts them all and protects us. But now our big protective brother has turned into a small baby. Say hi to a bunch of asteroids. Oh, and say bye-bye to Jupiter. This planet is known for its thick, swirling atmosphere. But with a weaker gravitational pull, Jupiter would probably have a hard time holding on to it. So over time, it would slowly escape into space, leaving behind a thin atmosphere composed mainly of nitrogen and oxygen. We'll also have to bid farewell to the iconic appearance of another giant, Saturn. The most noticeable difference would be the disappearance of its famous rings. Made up of small particles of ice and rock, the rings are a unique feature of Saturn. But with Earth's gravity, they would either fall onto the planet or scatter into space. Bummer. Saturn is also a gas giant, just like Jupiter. Its atmosphere is made up of mostly hydrogen and helium. But if it were Earth-sized, its gases would be compressed due to the increased gravity. This would make it much denser. That means Saturn's overall size and shape would change. Theoretically, if we squeeze Saturn hard, it could potentially become a brown dwarf. It's a type of failed star that lacks the mass to sustain nuclear fusion, but emits heat and light. So, Saturn could stop being a planet altogether. The weather on it would probably have changed too. All its crazy storms, such as the famous hexagonal storm at its North Pole, would have become weaker and calmer. The next giant is Uranus. Let's try to compress this poor fella. First off, the surface gravity on Uranus would be much weaker than it is now. Its atmosphere might also change. If Uranus was smaller, it could have a thinner atmosphere and different gases altogether. This planet is pretty chilly, with an average temperature of negative 353 degrees Fahrenheit. Blah! But if it was the size of Earth, it might actually warm up a bit due to its reduced volume to surface area ratio. Don't get too excited though, it would still be way colder than the coldest spots on Earth. As you can see, gas giants don't easily go through all this shrinking, except perhaps one of them. Surprisingly, small Neptune would become much friendlier. For starters, it would probably be a rocky planet with a tiny atmosphere. That means no more gas giant, but instead, a planet that's easier for humans and critters alike to live and move around on. Speaking of movement, because of the smaller size, the gravity on this new Neptune would be almost the same as Earth's, making it a heck of a lot easier to walk and jump around. No more floating away into space. Now, the atmosphere of the original Neptune is so thick you could barely see your hand in front of your face. And the surface pressure is about 100 times that of Earth's atmosphere. But our new Neptune would be much different, with a much thinner and less dense atmosphere. It would still have some methane, water, and ammonia in it, but nowhere near as much as before. Finally, the temperature. The current Neptune is freezing, with an average temperature of about negative 370 degrees Fahrenheit. But if it was the same size as Earth, it would likely be much warmer, just like Uranus. Ah, that's more like it. What a planet that would be. That's it for the changes in the planets. But what would happen to the entire solar system if we made all the planets so small? It's hard to predict, but it's clear that their gravity and orbits could change a lot. It's unlikely that any of them would have flown into outer space, or crashed into each other, or something like that. But many of their orbits would probably become quite unstable, and the number of collisions with asteroids would have increased significantly. Of course, all this is purely speculation. It's not like we can actually test all this. But it's still a pretty interesting thought experiment, and it makes you appreciate just how unique and special our solar system really is.
Okay, show of hands. Who still believes that the sun goes around the Earth? Nobody. Oh, but everybody used to. It sure looks like it does. The sun comes up in the east, the sun goes down in the west. The sun comes up in the east again, so the sun goes around the Earth. It seems intuitively irrefutable, and it is so. But it's not true. The sun doesn't go around the Earth. Everybody knows that, but only now. So why do people still believe the moon goes around the Earth? It's not true either. We have to go back over 500 years to begin to get an idea of how hard it is for science to change universally accepted facts. Nicholas Copernicus, around 1510, was the first to propose a heliocentric, sun-centered solar system, but he didn't do it publicly. Copernicus privately circulated letters to other astronomers explaining why the accepted fact of an Earth-centered solar system should be scrapped in favor of a more straightforward, more astronomically correct, sun-centered solar system. Copernicus's difficulty in promoting the sun-centered solar system depended on another bold conceptual innovation, that the Earth rotates. Copernicus's concept of a rotating Earth flew directly in the face of 5 literal statements in the Bible that the Earth was founded on a fixed foundation never to be moved. And the Catholic Church wasn't about to let that worldview be challenged or changed. Copernicus had too much to lose to go public with his revolutionary, pun intended, heliocentric theory as a churchman himself. 100 years later, Galileo Galilei wasn't so reticent. Galileo had observational proof to back him up because he had a telescope. In early 1610, Galileo first observed the moons of Jupiter and kept track of their orbits. Yes, the moons of Jupiter do orbit around Jupiter. They go round and round the giant planet in actual orbits, unlike, as we shall soon see, how our moon travels around the sun with the Earth. Galileo became famous, or infamous, as the case may be, because he discovered orbital motions that were not heliocentric, that did not fit the accepted worldview. It rattled civilization's Earth-centered cosmology. Galileo was indeed revolutionary. Later in 1610, Galileo observed through his telescope, which only had an aperture of 1.5 inches, the planet Venus going through phases, just like the moon goes through stages. Galileo wrote that Venus imitates the moon, in Latin, in his notebook. There could be no other explanation for these observations. Venus was orbiting the sun. People were afraid to look through Galileo's telescope when he set it up in the Great Square of Pisa. They were too scared to have their worldview revolutionized. Strange as it may seem, we are experiencing something similar to that now concerning the moon orbiting the sun and acting like a double planet with Earth. People, scientists included, stubbornly persist in viewing the moon as its clever official International Astronomical Union name. It's a moon of the Earth, orbiting around the Earth, showing its different phases throughout the lunar month, or moonth, as moon fans sometimes like to call the 29.5-day cycle of lunar phases. Moon lovers' favorite day of the week, of course, is Moon Day. It comes right after Sunday. But back to the science. It's how our school books portray the phases of the moon. It's what people believe now. Notice how the Earth is the moon's center, and how it goes around the Earth in a circular path. This is the geocentric view of the moon. It's what we see from Earth. The moon comes up, the moon goes down. The moon comes up again. The moon goes around the Earth. But that's not what's happening in space. It's way past time we Copernicus-size the moon. We need to start seeing the moon from a heliocentric point of view, as we do for everything else in the solar system. First of all, the geocentric view of the moon's phases shows the Earth stationary, sitting in the center of the moon's path for a whole month. But the Earth is not stationary at all. We're zooming around the sun at a very high speed, anywhere between 66 and 68,000 miles an hour. Therefore, any picture of the moon going around a stationary Earth is profoundly misleading and really outright wrong. The heliocentric view of the Earth and moon moving together in space should look something like this. Notice that the moon is not going around the Earth. It's traveling along with the Earth, around the sun. The path of the moon around the sun is a sinusoidal path back and forth, across the ever-forward moving path of the Earth. Notice that the moon always goes forward too. It doesn't ever go backward to either the sun or the Earth. By always moving forward and sinusoidal, the path of the moon does not qualify as an orbit in the same sense that the other moons of the solar system orbit their planets in elliptical paths. Therefore, it is wrong to say the moon orbits the Earth. The moon orbits the sun along with the Earth, or the moon and the Earth both orbit the sun, are statements Copernicus and Galileo would approve of. But science today has difficulty accepting a heliocentric view of the moon. Maybe there would be too many books that need to be reprinted. Maybe too many astronomy professors would have to admit that they were wrong their whole careers. Accordingly, objections are put forward to block the revolutionary heliocentric view of the moon from being universally accepted. One such objection is that the moon never leaves the Earth's gravity well, and therefore should be rightly considered a moon of the Earth, an orbital, to use the astronomical term for satellite. Undoubtedly, the moon never leaves the Earth's gravity well, or else we would lose the moon. However, representations of this well-known definite fact always show the moon moving around the Earth inside the gravity well, and this is not true. The moon never goes back toward the Earth as it would need to if it were in an elliptical orbit. So the gravity well objection can be dismissed because the astronomers who propose as orbital evidence that the moon always stays within the Earth's gravity well fail or neglect to include the facts of the moon's continuously forward sinusoidal motion. Escape velocity for the moon to leave Earth's gravity well is reported to be about 2,684 miles per hour. Relative to the Earth, the moon presently moves about 2,238 miles per hour. What kind of impact would it take to accelerate the moon that extra 450 miles per hour needed to knock it out of Earth's gravity well? If anyone wants to compute that, you're most welcome to put your answer in the comments section. Maybe it could happen, and that would not be good. There's another objection to looking at the moon from a heliocentric point of view. And that involves the barycenter of the Earth-Moon system. The barycenter is the center of gravity between the Earth and the moon. Think of yourself on a seesaw in the park. The other end of the seesaw is a massive lineman from a professional football team. How far forward towards you would the lineman have to move so that you both are balanced evenly? He'd have to move toward you almost to the center of the seesaw. You are the moon, and the lineman is the Earth, although Earth is a feminine name. The balance point of the Earth-Moon system, the barycenter, is over 1,000 miles inside the Earth. It is this balance point, astronomers dutifully point out, that is orbiting the Sun. It is a heliocentric point of view. Copernicus and Galileo would approve. However, these astronomers always seem to add the geocentric animation of the moon orbiting around the Earth, with the barycenter inside. In this way, they can keep the moon orbiting around the Earth. But it's somewhat dishonest to combine two different perspectives in one animation. You can't have your cake and eat it too. This leads us directly to the real sticking point that keeps us from believing that the moon is orbiting the sun, the double planet conundrum. The International Astronomy Union refuses to consider the moon and Earth a double planet. They refuse to do so almost exclusively because the barycenter of the Earth-Moon system is inside the Earth. It's tough to buck City Hall, as the saying goes. You'll recall that IAU, or UAI if you use the French designation, demoted Pluto to dwarf planet status. And they still haven't reversed that decision, despite seemingly ample evidence that Pluto is the 9th planet. Perhaps we should reflect on what it means to be an Earthling. To be an Earthling implies that we know ourselves to be spaceborne people orbiting a yellowish star near the outskirts of a spiral galaxy. We, meaning all the peoples of Earth, live in space and are absolute creatures from space. Above us is the moon, Earth's companion. We're making a big mistake by referencing the moon according to our geocentric parameters. Our conceptual expansion into space is inhibited by an incorrect, outdated, earthbound view of the moon. The universe doesn't revolve around us, and neither does the moon.
Doctor, I can't understand what's going on. I feel dizzy and, how do I say it? I'm tilting. It didn't happen overnight. Like, I didn't wake up and couldn't stand straight. No, one day, I felt that my axis had shifted by 1 inch. Another day, it was 2 inches. And once, you won't believe it, it was 31.5 inches. That's alarming. What if I accidentally turned upside down and all my inhabitants fall off my surface? Ah, dear Earth. We ran some tests and are ready to explain an unfortunate combination of factors that has affected your axis. The last one will perhaps be the most unexpected and upsetting. It all started back in March 2011, when a devastating magnitude 9 earthquake struck off the coast of Japan. It was so powerful that not only did it shift Earth's axis, but it also shortened the length of the day. This earthquake displaced our planet's axis by approximately 6.5 inches and may have moved Japan's main island by about 8 feet. Like other similarly massive earthquakes, it also altered Earth's rotation speed. To make it easier, let's compare it to a spinning ice skater. When a skater pulls their arms close to their body, they spin faster by concentrating their mass near the axis of rotation. Something similar happens during the most powerful earthquakes. They shift Earth's mass closer to its rotational axis, causing it to spin faster and shortening the day length. The calculations showed that the Japanese earthquake sped up Earth's rotation by about 1.8 microseconds, which is about 1.8 millionths of a second. Not a big deal, but at the end of the day, every nanosecond counts. For comparison, the infamous Indonesian earthquake shortened the length of a day by 2.68 microseconds. It struck on December 26, 2004, at 0:58 UTC. The epicenter lay off the western coast of northern Sumatra, Indonesia. This powerful undersea earthquake triggered devastating tsunamis that swept across the Indian Ocean, causing widespread destruction and immense loss of life in countries like Indonesia, Sri Lanka, India, and Thailand. Even coastal areas as far as East Africa had severe damage. The Earth's magnitude, initially recorded at 9.0 on the Richter scale, was later adjusted to between 9.1 and 9.3, making it the most powerful earthquake ever recorded in Asia. The faulting, that's when Earth's crust completely breaks and its parts slide past each other, lasted between 500 and 600 seconds, and it was the longest duration ever observed. The immense force of the quake caused the entire planet to vibrate by at least half an inch and triggered other earthquakes as far away as Alaska. All that immense energy the earthquake released caused subtle but quite measurable changes to Earth. The shift in mass slightly changed the planet's rotation, shortening the day. It also caused a small wobble in Earth's axis from 1 to 2.4 inches toward 145° east longitude. So, when it comes to changes in Earth's rotation speed and axis, it's all about the redistribution of mass. This can happen naturally through disasters, but human activities can also trigger it. Take the Three Gorges Dam, for instance. This massive structure across the Yangtze River in China's Hubei province may seem to be an engineering triumph, but it's pretty ambiguous. Finished in 2012 after nearly 20 years, this massive dam is 7,660 feet long and 607 feet high. And yes, it is so big that it can affect the way our planet spins. Its reservoir is capable of holding 9.5 cubic miles of water, has enough mass to slightly alter the Earth's rotational inertia, slightly slowing the planet's rotation. According to NASA, the Three Gorges Dam reservoir could shift Earth's pole position by almost 1 inch and increase the length of a day by 0.06 microseconds. Dams aren't the only worry. If polar ice melts, water rushes into the oceans, hiking up sea levels, especially near the equator. This mass shift slows Earth's spin way more than dams do. You won't feel it day to day, but it can affect ultra-precise equipment, such as atomic clocks. To fix this, scientists suggested a negative leap second, making a minute 59 seconds, to balance Earth's spin changes. Okay, so you're thinking you've got nothing to do with all those tilts. You don't build dams, right? Bad news. If you take regular showers, you're part of it too. Every time you turn on the tap, you're affecting Earth's tilt just a tiny bit. Thing is, our planet is always shifting and adapting, so even small actions like using water can influence its orientation. Over the past 2 decades, groundwater pumping has caused the Earth's tilt to shift by 31.5 inches. This water redistribution is equal to about 0.24 inches of sea level rise. It turns out that among climate-related causes, groundwater redistribution has the largest impact on the drift of Earth's rotational pull. But what is groundwater? It's the water stored beneath the Earth's surface, filling the spaces in soil, sand, and rock. It comes from rain and other precipitation that seeps into the ground, collecting in underground reservoirs, aquifers. Unlike rivers and lakes, groundwater stays below the surface, acting like a natural water reserve. Thanks to it, we have a steady supply even during dry periods. Many people, especially in rural areas, rely on groundwater as their main source of drinking water. Farmers use it to irrigate crops, while industries depend on it for manufacturing and cooling systems. It sounds pretty harmless, doesn't it? How can something so useful cause our planet to shift? Well, a study covering data from 1993 to 2010 revealed that we've pumped about 2,150 gigatons of groundwater in that time. And this large-scale water removal has shifted the Earth's tilt and rotation. After we use groundwater, much of it eventually flows into the oceans, contributing to rising sea levels. In areas like Western North America and Northwestern India, people use a lot of groundwater, and it may have a connection to these shifts. Yikes, let's face it. All these findings are rather disturbing. But understanding the impact of groundwater use is already a huge step in the right direction. Hey, I'm not done yet. This tilting issue isn't just about stuff happening on Earth. We also need to look at space. We've talked a lot about water, right? Well, you know that the moon has a big role in that. Its gravity is super important for forming tides and all that. So one more thing that affects our planet a lot is the gradual movement of the moon away from Earth. These two bodies interact gravitationally, which makes Earth's rotation slow over time, even though significant events like earthquakes occasionally speed it up temporarily. How did we figure it out? Glad you asked. Once, someone paid attention to ancient corals. After analyzing them, scientists realized that Earth had once rotated much faster. The thing is, corals grow by laying down thin layers of calcium carbonate. They do it daily, and variations reflect seasonal changes. By counting these layers, scientists have calculated the number of days in a year millions of years ago. They found that Earth had about 420 days per year 444 to 419 million years ago. But over time, the moon's influence had caused Earth's rotation to slow. And now we only have 365 days in a year. I feel robbed, At the moment, the moon is moving 1.5 inches away from Earth each year. That's about the same speed at which your fingernails grow. Astronomers have figured it out with the help of special mirrors placed on the moon during the Apollo missions. For over 50 years, researchers have been sending laser beams to these mirrors and measuring the time it took for the light to bounce back. In any case, dear Earth, at the moment, your condition isn't critical. As for your inhabitants, they won't fall off your surface. All thanks to your gravity, pulling them toward your center. Just don't switch it off, and everything's gonna be fine. About a century ago, people envisioned the 21st century as a time filled with quirky inventions. They weren't far off the mark. We're now one step closer to establishing an actual settlement on the moon. Before we can create a new home up, we need to find a way to stay connected, beyond just transportation and shipping. Being able to send a simple text, even something as casual as, "Hey, how are you?" is essential. We can't move to the moon if we're cut off from Earth. Let me spill some tea. A lunar 4G network is currently being developed. The company leading this initiative is none other than Nokia's Bell Labs. The company, bought by the world-famous Finnish company that started out as a paper mill in the 19th century and later ventured into the cell phone industry, creating iconic devices long before Apple launched its first phone. Once the network is completed, it will be loaded onto a lander, deployed, and connected using specialized radio equipment. But don't think this is just a fun experiment. It has significant purposes. The Lunar Outpost rover, one of the vehicles involved in this mission, will thoroughly explore an area known as the Shackleton Connecting Ridge. Another rover, the Micronova, will investigate a lunar crater in search of ice. When they discover ice and capture images, this information will be first transmitted to the lander and then relayed to Earth, an unprecedented achievement in history. Moreover, the importance of a reliable phone connection cannot be overstated. Currently, astronauts communicate via radio. But NASA aims to establish a lunar communication system capable of supporting high-resolution video. Effective communication during space missions is as crucial as food and water, and with this new lunar 4G technology, video calls on the moon could soon become a reality. Plus, thanks to lunar 4G, we'll be able to track how the endangered species sent to the moon are doing. Oh, sorry, I completely forgot to mention something important. As more species edge closer to extinction today, scientists are collecting samples from animals, plants, and other organisms to store in biorepositories around the globe. Unfortunately, the conditions on Earth are far from ideal for these modern-day Noah's Arks. Hence, the decision to build 1 or 2 vaults on the moon makes perfect sense. On the moon, there's a permanently shadowed region at its south pole. It may seem like a fortunate coincidence, but some lunar craters may meet the criterion of temperature, -320 degrees Fahrenheit, which is precisely what we need for long-term self-storage. Initially, the plan was to construct the vault in lava tubes that run beneath the moon's surface, but that would have posed significant risks. This design requires a special solar-powered cooling system, and any accidental loss of power could be catastrophic, resulting in the destruction of all the samples. However, if we built it in a forever frozen shadowed area, the vault wouldn't need any energy or human maintenance. Bingo! It sounds almost too good to be true, and indeed there are several complications. For instance, dust is an omnipresent issue on the moon, infiltrating everything. If the storage requires seals, a dust mitigation system must be developed, which has not yet been created. So for now, it remains a theoretical concept rather than a practical solution.
40, 50 feet, why don't you turn around and let them get a view from there and...
I know you want to learn about real things, not just concepts. Here's something real for you. The moon is full of human waste, carefully packed into bags. According to estimates, there are around 96 of these bags you'd probably prefer to never open. But you never know what exactly is hidden inside. It could be any product of the human body out there. So, if we ever make it to the moon and you accidentally stumble upon a mysterious bag, my advice is to resist the urge to open it. Instead, you can hand it over to scientists. They say they're eager to get their hands on them. Humans are incredible, in a rather unfortunate way. We haven't even established a proper settlement on the moon yet, but there's already around 200 tons of junk scattered about. It piles up there as if it were a teenager's room rather than a celestial body. Alongside those rather unappealing human waste bags, you'll also find cameras, drills, towels, brushes, rakes, a multitude of other technical items, and surprisingly, a falcon's feather. I'll explain that in a moment. At the end of Apollo 15's final moonwalk, David Scott pulled out a falcon's feather and a hammer to demonstrate Galileo's theory that in the absence of air resistance, different objects fall at the same rate. Amidst all that junk, there's an actual piece of art, so we could say that the moon, if it doesn't have the very first art museum, at least boasts a small exhibition. The crew of Apollo 15 took a 3.5-inch tall aluminum figure to the moon. Created by a Belgian artist, it's called the Fallen Astronaut, and it was laid on its side with a plaque listing the names of astronauts and cosmonauts who contributed to exploration. But the list of odd objects on the moon doesn't end there. If you ever find yourself in need of cash, you can find it on the moon, since a stack of $2 bills was simply forgotten there. Yep, a lot of material has been collected since 1969, when humans first stepped on the moon.
It's one small step for man, one giant leap for mankind.
Our natural satellite was first seen in a telescope in 1609. But what about its true age? To understand that, we need to start with how the moon first formed. Back in the mid-80s, a conference in Hawaii brought together a bunch of scientists to figure out where the moon came from. They came up with a pretty cool idea. The moon probably formed with the stuff that our planet Earth donated. Picture this. A Mars-sized object crashed into the early Earth, flinging molten materials into space, which eventually came together to become the moon we see today. This theory clears up a lot of mysteries. For instance, it used to baffle folks why the moon has such a small iron core. The answer is simple. It formed from Earth's outer layer, which isn't rich in iron. And that pale crust of the moon? It's just minerals that floated to the top when the molten moon cooled down. At first, the moon was super close to Earth, but it's been slowly drifting away at about 2 inches a year, even while you're watching this video. Figuring out when this all went down, though, is a bit tricky. The Apollo astronauts brought back a bunch of moon rocks, which helped scientists estimate their ages. The oldest ones are around 4.35 billion years old, which is about 200 million years after the solar system kicked off. So, here's the thing. There's no exact date for when the moon formed, but there are several interesting theories. One idea is that the age of these rocks could mean the moon is around 4.35 billion years old. But some scientists who look at how planets form think that most of the material in the early solar system came together way before that 200 million year mark. They argue that a big impact that created the moon happening that late seems pretty unlikely, which means the moon could actually be older than 3.5 billion years. Another interesting thought is that the moon might have gone through some serious heating events as it moved away from Earth. This is similar to what happens on Io, one of Jupiter's supervolcanic moons. The gravitational pull from a bigger body can stretch and compress a smaller one, generating heat, like when you squeeze a rubber ball. The rocks on both Io and the moon warm up this way. Rocks have radioactive elements that act like internal clocks, helping scientists figure out their ages. The catch is, if the moon heats up too much, it resets those clocks and only starts keeping time again once it cools down. So those rocks that are about 4.35 billion years old might not actually mark the moon's birthday. They could just indicate a time of tidal heating. This suggests, once again, that the moon had to have formed even earlier than that.
You fly away from Earth at a safe distance in your super modern spaceship, and then bam! You travel faster than the speed of light in interstellar space. How cool! The light from thousands of stars rushes past you. A few minutes, and you're on the other side of the Milky Way and going to work. Such travel has long been common for humans, for you are a member of the human civilization that has conquered the entire galaxy. But it took almost 90 million years to get there. So how did we achieve this? It's like a computer game. In the beginning, we had a fleet of 3 motherships that could travel at 310 miles per second. Each of them had 10 colonization pads. The ship could undock a pad and drop it on the desired planet. We also had 2 speed ships that traveled twice as fast but could only colonize 1 planet. Each colonized planet could send 1 new ship on an expedition. So humanity was able to spread across the galaxy in 90 million years. Most of that time was spent flying from star to star. So the main problem of colonization is speed. Year 2021. Our spaceships can now fly at about 24,850 miles per hour. That's enough speed to travel from New York to Los Angeles in less than 4 minutes. But a trip to neighboring planets like Mars still takes about 7 months. The nearest star to the Sun, Proxima Centauri, is 4.2 light-years away. That means light, the fastest thing in the universe, takes 4.2 years to get there from the Sun. It would take our rocket 73,000 years to get there. That's longer than an advanced human civilization has existed. And our galaxy, the Milky Way, is 105,000 light-years wide. So even traveling at the speed of light would take forever. So, naturally, humanity came up with other ways to travel. Let's move into the future and imagine that we've solved this problem. We started accelerating with microscopic probes propelled by a directional laser beam from Earth. This made it possible to reach speeds of 25% of the speed of light, still very slow. The problem was that nothing that has mass can travel at the speed of light. So we moved on to the Alcubierre drive study. This method doesn't involve moving from point A to point B, but instead compressing the space between those points. Here's a piece of checkered paper. Imagine that you need to travel 3 squares to your destination. Instead of moving in a straight line as fast as possible, we squeeze these squares so that our spaceship is at point B. Now we unsqueeze them back. Space is normalized and we've traveled, in fact, standing still. This is how the Alcubierre drive works. It compresses space in front of the spaceship and expands it behind its tail. So, theoretically, an Alcubierre drive spaceship can move at any speed, even faster than the speed of light. But the amount of energy needed to do this is enormous, and it could be compared to the mass energy of the entire planet of Jupiter. So, while some scientists were working to improve the Alcubierre drive, others were looking inside the most mysterious object in the universe, a black hole. A black hole is something so heavy that it attracts even light and won't let it go. Imagine a circular trampoline. This is our space-time. We put a basketball in its center. The trampoline sags a little bit. Now all the objects we put on the trampoline will roll toward the basketball. That's how gravity works. But if you roll the golf ball past the basketball, it has a chance of getting out of this funnel. Now put a heavy bowling ball in the center of the trampoline. The trampoline sags even more. Now the golf ball will inevitably fall into the funnel with the bowling ball with no chance of escape. That's how a black hole works. And some scientists believe there may be a wormhole at the heart of a black hole. It's a shortcut between point A and point B in the universe. Back to our piece of paper. Instead of moving straight ahead, we fold the piece so that point A is right above point B. Now we make a hole in the paper and move to point B. We unfold it back and voila! You've arrived at your destination. So there's a theory that if a spaceship enters the black hole's gravitational field and withstands the incredible stress there, it can exit to any other point in the universe which that wormhole led to. It might even be another galaxy, or even a parallel universe. Well, our research was successful, and now, looking at a map of the Milky Way, we can get to absolutely anywhere. All that remains is to choose the right place to colonize. There are about 1 billion stars. Around each of them are planets possibly suitable for life. So we need to narrow down the list. First, we look for relatively young stars, almost like our Sun. Near them, a human colony can potentially live for a long time. After that, when a star gets old, it begins to expand and turn red. In the last stages of its life, it can absorb all the planets around it and then explode with such force that the light from the explosion can be seen dozens of light years away. Secondly, the candidate for a human colony must be in the habitable zone of the star. It's a sweet spot, not too far away from and not too close to the star, so that it's not too cold or too hot there. In other words, water on the planet must exist in liquid form. Also, the candidate planet must have a solid surface so that we can live on it. Another important factor is the size of the planet. If it's too big, its gravitational force will press on us. It'll be harder for us to jump, walk, and lift weights on this planet because we're used to the Earth's gravity. But if the planet is too small, we'll feel like real strongmen there. We'll be able to jump high and lift large weights. But then our muscles will lose tone and our health will deteriorate. So, we're looking for a planet about the size of Earth. Altogether, we have about 100,000 star systems that fit our parameters, so we start exploring and colonizing. And here's our first target. We've named this planet New Home. Clever. We fire up our faster-than-light engine, and bam, we're there. Even though this planet fits all our criteria, it's still hard to call this place home. Desert landscapes with lots of craters and canyons. We'll have to work hard to make this place look like Earth. The terraforming phase of the planet is about to begin. That means we're going to change the climate and the atmosphere here. We need about 78% nitrogen and 21% oxygen so we can breathe here without spacesuits. So we're launching air plants. Other plants will produce water. We're also building power plants and a plant to produce fuel for our spacecraft. Last but not least, food extraction. Once everything is ready, the colony here can exist on its own. And after several centuries, this planet will be developed and populated enough to send an expedition to colonize neighboring worlds. So, for many millions of years, humanity has been weaving its web in the Milky Way. From one planet to another, we've colonized our galaxy. Humanity is now not only multiplanetary, but also interstellar. The next goal is to make us an intergalactic species. The fastest wind speed ever recorded on Earth was related to a hurricane gust. On April 10, 1996, tropical cyclone Olivia was passing by Barrow Island, Western Australia. At one moment, the storm reached the speed of a Category 4 hurricane, 254 miles per hour. That's faster than a Formula One racing car. You can probably imagine how much damage this kind of wind can cause. The only windstorm faster than that is a tornado. The air inside a whirlwind can move at a speed of 300 miles per hour. Unfortunately, there's no sure way to measure tornadic winds. Weather instruments never survived the experience. Oh, and licking your finger and sticking it up in the wind to measure speed also isn't a good idea here, unless you don't mind losing your arm, or worse. Here are some more numbers. 35 miles per hour and more, that's the speed of the average blizzard. 50 to 60 miles per hour, that's how fast a severe thunderstorm moves. More than 74 miles per hour is the speed of a powerful tropical hurricane. Up to 400 miles per hour? Wait, do such speeds exist? Yep, but you need to travel to Jupiter to see a storm that speedy. The Great Red Spot is an enormous storm raging in the southern hemisphere of the gas giant. Its top parts are towering more than 5 miles above the surrounding cloud tops. The storm's almost 3 times as wide as our planet. In 2017, NASA's Juno space probe managed to collect lots of data about the red spot, and it turned out that the monster of a storm went more than 200 miles down into the planet's atmosphere. That's 30 to 100 times deeper than any ocean on Earth. But since these measurements were most likely imprecise, the storm's true roots can be reaching even deeper. The Great Red Spot is colder than the rest of the atmosphere, and Jupiter's temperatures are minus 234 degrees Fahrenheit in its upper cloud layers. The closer it is to the core, the hotter it gets. But the highest temperatures ever recorded on the planet were in the atmosphere right above the Great Red Spot. There, the heat can reach 2,400 degrees Fahrenheit. That's hotter than lava on our planet. The storm's extreme conditions and turbulence produce gravitational and sound waves. These waves might be responsible for the superheating. The storm itself is also warmer at its bottom than at the top. If you found yourself at its center, you wouldn't be too impressed. But on the edges, the wind speed reaches 300 to 420 miles per hour. That's faster than Earth's tornadoes. Now, this will help you picture the immense force of such winds. On Earth, the wind doesn't have to be faster than 60 miles per hour to lift a person as heavy as 170 pounds from the ground. A wind as fast as 75 miles per hour can uproot large trees, peel off roofs, break windows, and turn over mobile homes. When the wind speed reaches 150, it can send cars flying. Now picture the havoc a storm as powerful as the Great Red Spot can cause on our planet. But could such an enormous anticyclone occur on Earth? Luckily, not. Our planet doesn't have the unique conditions needed for the storm to form. Scientists faced lots of challenges when they were trying to understand the mystery that was the Great Red Spot. And it was mostly the fault of the storm's home planet. It's more than 1,000 times larger than Earth and over 300 times as massive. Jupiter is a gas giant, which means it consists mostly of fill in the blank. Around the planet's core, there's an ocean of liquid hydrogen. And the atmosphere is also mostly made up of hydrogen and helium. That means Jupiter doesn't have any solid ground, the only thing that could make the storm weaken. Without any friction, the storm has already been churning for centuries. The hot gases in the planet's atmosphere are always moving, rising, falling, and swirling. Just like on our planet, when cooler and hotter gases mix and merge into one another, they form giant circling storms. Astronomers think that once, several enormous storms came together and created the Great Red Spot. And now, it keeps raging by constantly drawing cool gases from below and hot gases from above. Plus, this monster of a storm absorbs other smaller vortices. They make the Great Red Spot even more powerful. Unfortunately, thick clouds on Jupiter don't allow people to see what's going on in the planet's lower atmosphere. Astronomers have been speculating on what may lie beneath the Great Red Spot for decades. Could it be a massive volcano? Unlikely. Jupiter's mostly gas. That's why it doesn't have a crust that could crack and release scorching hot stuff from the planet's interior. Several theories try to explain why the storm has its trademark color. It varies from whitish and pale salmon to orange and brick red. Some scientists believe the answer lies below the Great Red Spot, closer to the planet's surface. A colorless layer of ammonium hydrosulfide might be reacting with cosmic rays or the UV radiation coming from the sun. This somehow gives the spot its pretty red color. but so far it's just a theory. Astronomers have been observing the Great Red Spot since the 1830s, and for the first time, the storm was spotted in 1665 and described as the permanent spot. In other words, the storm is almost 400 years old. Strangely, it's been shrinking in size since the beginning of the 21st century. In 2019, it began flaking at the edges, with smaller pieces breaking off and vanishing. If this process continues, by 2040, the Great Red Spot will become circular, or it may disappear altogether. The storm isn't only getting smaller, it's also growing taller and getting a more intense orange hue. It's not completely clear why it's happening. Might be because of a chemical reaction. It occurs when some new material rises to the top layers of the atmosphere from below. The Great Red Spot might be the most famous storm in the solar system, but it's by no means the only one. Even on Jupiter, there's a bit less known Little Red Spot, one more anticyclone but smaller in size. Well, when I say smaller, I mean the thing's not as large as its big sister, but it's still about the size of Earth. Recently, the highest wind speed inside the Little Red Spot has increased up to 400 miles per hour. A storm as wide as our planet rages on Saturn. It's called the Great White Spot. The storm has a tail of white clouds encircling the entire planet. It occurs every 30 years or so, when Saturn's northern hemisphere tilts toward the Sun. This storm indeed starts as a spot, but then it stretches in length. Astronomers have figured out that the Great White Spot is actually a huge system of thunderstorms. At the peak of the storm, lightning can flash more than 10 times per second. But the main mystery about the Great White, it's where it gets its energy from. Some scientists think it may be powered by the sun. Others argue that the storm's cloud pattern only makes sense if there's an internal heat source that can power the winds. Great dark spots on Neptune are massive storms that form in areas with high atmospheric pressure. That's different on Earth. Here, storms appear when the pressure is low. Around the spot's edges, the wind speeds can reach 1,300 miles per hour. Astronomers have observed 6 dark spots on Neptune so far. These powerful storms get born deep in the planet's atmosphere, and the darker a storm is, the brighter the methane clouds around it are. Another monster-sized storm raging on Saturn looks pretty much like a hurricane or typhoon on our planet. It has an eye and spiraling clouds surrounding it. But compared to Earth's hurricanes, the one on the ring planet is titanic. On Saturn, the eye of the storm is up to 1,250 miles across. The bright clouds closer to the edges of the hurricane are moving at a speed of 330 miles per hour. But one of the most unusual things about this storm is its shape. It has 6 sides and is known as the hexagon. When astronomers saw the first images with the vortex, they did a double take. The thing was just too similar to our storms. And still, the one whirling on Saturn has an eye that's almost 20 times larger than any people have seen on Earth. The storm also moves 4 times faster than hurricane winds on our planet. Saturn's atmosphere has little water vapor. How the bizarre hexagon storm is getting by in such conditions is a mystery. Plus, unlike the constantly drifting hurricanes on Earth, the one on Saturn seems to have nowhere to go. For some inexplicable reason, it's stuck at the planet's North Pole.
Tell me the truth. You probably think that Earth's magnetic field is caused by a big ball of solid iron in the middle of the planet, right? Yep, I mean the inner core. But the problem here is that in the inner core, the temperatures are so high that the very magnetism of iron itself is changed. Once such a temperature, which is called the Curie point, is reached, atoms aren't able to align to a magnetic point anymore. So, in reality, Earth's magnetic field is created by the swirling outer core, and magnetism there is more than 50 times greater than it is on the surface. The liquid iron in the outer core conducts electricity
perfectly, which helps it create electrical currents driving the magnetic field. Without it, our planet wouldn't be able to hold onto its atmosphere. As a result, we'd lose our main protection from extremely dangerous space radiation. But it wasn't the outer core that surprised us not so long ago. Scientists say Earth's inner core has likely stopped rotating relative to the mantle and the surface of the planet. Even more exciting, it could even go into reverse. But let's look into the details. Earth is formed of the crust, mantle, and outer and inner cores. The solid inner core is about 3,200 miles below the crust. It's separated from the semi-solid mantle by the liquid outer core. Yep, the one thanks to which we have the magnetic field. And since this outer core is liquid, it allows the inner core to rotate at a speed different from the speed of our planet's rotation. Earth's core has a radius of 2,200 miles and is almost as large as Mars. It mostly consists of iron and nickel and makes up around 1/3 of Earth's mass. The spin of the inner core is powered by the outer core. It turns out that the slowing of the core started in 2009. Since that time, seismic records, which had previously been changing continuously, have shown little difference. And it makes scientists conclude that the inner core's rotation has paused. But we're nowhere near the scenario of a disaster movie. Apparently, the inner core taking a temporary break is part of its 70-year-long cycle. During this cycle, the core switches directions every 35 years or so. This might influence Earth's magnetic field and the length of the day, but some researchers are skeptical about it. And some scientists even go as far to say that the inner core isn't moving at all. Okay, but what would happen if Earth's core indeed stopped rotating? Well, if it was the solid inner core, the answer would be nothing dramatic. Even if it didn't just reverse the direction of its movement, like it's doing at the moment, but stopped altogether, it would just impact the speed of Earth's rotation. It'd slow down, making our days longer. Plus, with time, it could probably degrade our planet's magnetic field, and it would be bad news. But not as bad as they would be if the outer core stopped spinning. As you already know, without this layer's rotation, Earth would have to kiss its magnetic field goodbye, and that's how the downfall of the planet would begin. Things would start getting shaky. The tectonic plates would begin to slam into each other. You know, like when you're going by bus and the driver suddenly hits the brakes and you end up flying into other unfortunate passengers? Yeah, like that. The sudden collision of tectonic plates would trigger destructive earthquakes along the plate boundaries all over the world. They would wipe buildings, bridges, and roads off the face of the Earth. Water systems, electricity, and phone lines would also be destroyed. But the worst would be yet to come. Without the protective magnetic field, cosmic radiation would start hitting the surface of our planet. These high-energy particles coming from the sun would come in contact with oxygen and nitrogen in our atmosphere, effectively destroying our ozone layer. This would allow even more cosmic rays to reach the surface of Earth. The radiation would damage all kinds of electronic devices and disable power grids. And the consequences would be disastrous, not only for people, but for all forms of life on Earth. The stationary core would make navigating the planet more difficult. People would have to start using trail maps again, since compasses would become useless. It would also make it harder, if not impossible, for migratory animals to find their way. Birds would keep losing directions, and turtles would fail to find beaches where they used to lay eggs. Luckily, we don't need to worry about this kind of apocalyptic scenario. The planet's outer core is very unlikely to stop anytime soon, if ever. Now, do you want to find out something cool? Then listen to this. Our planet's inner core has a core of its own. Scientists have made this discovery just recently. They've learned that this core in the core could have developed around 500 million years ago as a result of some dramatic geological changes. What about other planets? Do they have the same cores as Earth? let's look at Mars, one of our planet's closest neighbors. Its heart is the size of the Moon. It's also almost twice as dense. Scientists made this conclusion after they got some data about the first observed Marsquake and meteorite impact. Both these events were captured by NASA's InSight lander, which had been monitoring seismic activity on the red planet for 4 years. The researchers also estimated that Mars's core is probably made mostly of a liquid iron alloy with a smattering of hydrogen, oxygen, and carbon. One day, Mars probably had a nice rotating core that supported the planet's magnetic field. There could be warm oceans swarming with life. But then, something must have happened, and on one terrible day, the red planet's core froze in place. It could have led to the weakening of Mars's once strong magnetic field. Its atmosphere was taken away by powerful solar winds, hitting the planet at a speed of several hundred miles per hour, and the red planet turned into a lifeless, dry desert. Now, what about gas giants? Let's take the largest and the most massive planet in the solar system, Jupiter. It's twice as massive as all other planets of the solar system combined. Almost 1,300 Earths could fit into this huge thing. Jupiter also has the shortest day in the solar system. It lasts a mere 10 Earth hours. At the same time, the gas giant needs 12 Earth years to complete an orbit around the Sun. Jupiter most likely appeared at the same time when the rest of our solar system formed, about 4.5 billion years ago. Probably the coolest thing about this gas giant is that it has the same ingredients as a star. But unfortunately, or should I say luckily, it hasn't grown massive enough to ignite. Scientists don't know for sure what Jupiter's core looks like. According to most theories, the gas giant has a dense core made up of heavy elements. During its formation, it was probably a collection of debris, icy material, and other small objects like comets and asteroids zipping around. Thanks to their mutual gravity, these bits of matter clumped together, forming larger chunks which later turned into Jupiter's core. At one point, it became massive enough to start attracting hydrogen and helium. More and more gases accumulated around the core until what we today know as Jupiter appeared. There's also a possibility that Jupiter doesn't have a core at all, or it might have existed once, but since then, it's eroded away. Hopefully, we'll find out the answers to these questions soon enough, since Juno, NASA's space probe, is orbiting Jupiter, collecting data about its gravitational and magnetic fields. So, what about the gas giant's magnetic field, you may ask? Does it even exist? Oh, don't worry. Jupiter is surrounded by a ginormous magnetic field called the magnetosphere.
Mars can be secretly messing up the depths of our oceans. The red planet is 140 million miles away from Earth, so we once thought that it couldn't have much of an impact on us. But that changed recently with the discovery of some kind of butterfly effect. What starts with a small gravitational pull in space ends up creating giant whirlpools down here. This suspicion began when scientists decided to explore almost 300 deep holes drilled in the ocean floor, which were made back in the 60s. Their goal was to understand the strength of deep ocean currents by analyzing sediments. Materials like sand or mud that accumulated at the bottom of the ocean over the last 65 million years. The bottom of the ocean has layers upon layers of sediments. When these layers show a continuous pattern, it means that the materials have been gradually layering over time without any sudden interruptions. In other words, deep currents were calm and stable. But the researchers also noticed a strange pattern. During specific time periods, they couldn't find any records of sedimentation, which means that something else was interrupting this process. The most likely reason for these gaps was the presence of intense currents at the bottom of the sea. Because they were so strong, they probably moved sediments from their original spots. But here's the weird part. All the gaps identified in the study occurred at intervals of exactly 2.4 million years. The data showed a total of 27 gaps, That can't just be a coincidence. So, the scientists realized they were not checking simple breaks in the sedimentation process, they were analyzing the presence of cycles. According to experts, the only plausible explanation for them lies in space and is probably the result of something known as the astronomical grand cycles. To understand this process, we first need to mention the Milankovitch cycles. They're named after the Serbian scientist who suggested a century ago that changes in the way Earth moves around the Sun and tilts on its axis can affect Earth's long-term climate. The thing is, the movements of Earth can be affected by many things, including other planets. Normally, our planet's orbit around the Sun isn't a perfect circle, but it's pretty close. However, from time to time, this path is directly affected by the gravitational pull of Jupiter and Saturn. So it's kind of like these two giant planets can pull our orbit, causing it to become more elliptical. Variations like this can affect the amount and distribution of sunlight, changing the climate here on Earth. According to the Milankovitch theory, Earth's climate patterns change in cycles of 405,000 years, 100,000 years, 41,000 years, and 23,000 years. And the theory is that these cycles might trigger the beginning and the end of glaciation periods, also known as ice ages. His theories were actually confirmed in the 70s by scientists who were also looking for evidence of these cycles in ocean floor sediments. Recent calculations have shown that besides the Milankovitch cycles, there are climate changes that follow much slower rhythms. They don't change every tens of thousands of years. Nope. We're talking about periods that stretch out over millions of years. And this is exactly what the astronomical grand cycles that I mentioned earlier are about. We know about such events basically because of evidence based on mathematics and computer modeling. But it is really hard to find any geological proof of the existence of these million-year astrological cycles, or any clue of how they affect Earth. That is, until now. Turns out, what scientists found at the bottom of the ocean could be just the proof we needed. And that's because the 2.4 million period lines up exactly with records of interactions between Earth and Mars. As the two planets chart their orbital paths, their gravitational fields interact in a process known as resonance. Yep, exactly like what happens with Jupiter and Saturn. From time to time, the gravitational forces of the red planet pull our orbit a bit closer to the Sun. And just like the shorter Milankovitch cycles, this grand cycle also affects our climate. In this case, by increasing the solar radiation that reaches Earth, making our planet warmer. To be honest, experts believe that this amount of extra solar radiation that Mars can somehow give us is not that big of a deal. I mean, it's not going to make our planet so hot that it will make us feel like we're stepping onto the Sun. But this slight difference in climate can be enough to change some behaviors on Earth, such as ocean currents. Warmer climates tend to produce more frequent major storms, and that often produces sediment-stirring eddies, also described as giant whirlpools, which can reach the seafloor at the deepest parts of the ocean, known as the abyss. Finding those gaps in the deep ocean sediment record is really impressive because it's probably the strongest evidence we have of the astronomical grand cycles. As I mentioned at the beginning of the video, it's all like the butterfly effect. Every 2.4 million years, Mars's gravitational pull shifts Earth's path around the Sun, causing our climate to warm up. And when the planet is warmer, it can lead to the formation of large whirlpools, which end up turning the deep ocean waters upside down. And there's one more thing. The cycles found in the research also line up with already known periods of warmer climate throughout world history, like the famous Paleocene-Eocene thermal maximum. This event took place around 56 million years ago, when Earth was warmed by about 14 degrees Fahrenheit. Loads of theories have popped up trying to figure this out, like a glitch in Earth's orbit or maybe the passage of a comet. But with this new study, it looks like Mars could also be involved in this event. These new findings are pretty convincing and exciting, sure, but scientists still need to do more work to link these possible cycles of climate change with deep-sea currents. I mean, they did a good job of finding an explanation for the sediment gaps, but so far, it's just a suggestion. Their success is really important for the whole scientific community, though. After all, knowing when exactly these astronomical grand cycles happen and how they affect Earth can help us a lot, especially to differentiate when climate change happens due to a natural event and when it occurs due to human intervention. Studying these whirlpools can also provide scientists with crucial insight into how climate change affects ocean circulation. So, another reason why this finding is so crucial has to do with the potential collapse of the Atlantic meridional overturning circulation. In short, this is a system of ocean currents that circulates water within the Atlantic Ocean, being responsible for bringing warm water north and cold water south. This is what brings warmth to different parts of the globe and also carries nutrients necessary to sustain ocean life. However, there are some fears that this system might stop or become too slow anytime soon. If that happens, oxygen-rich surface waters would no longer mix with deeper waters. But the good thing is that this possible link between Mars and Earth gives a positive take on this situation by suggesting that in a warmer world, more intense deep ocean currents may prevent our seas from stagnating. But again, it's just a suggestion. The evidence is still thin. Some skeptical experts like to point out that although eddies have indeed become more active over the past few decades, satellite observations have shown that their currents aren't always able to reach the seafloor and maintain an effective water circulation. For now, all we know is that it's hard to say who is right. Only the following studies will tell. Back in the day, from 774 to 775, Earth got hit with a mega blast of radiation. This crazy burst of energy left its mark. 3 rings from that year show way too high levels of radioactive stuff. But what exactly caused it? Scientists are inclined to think that the reason was a solar flare. Some folks think maybe a massive supernova caused the radiation blast. But astronomer Phil Plait says that if that had been the case, it would have had to be less than 1,000 light years away and would have been crazy bright. But there's no record of that happening. No bright, shiny Death Star in sight. After looking at the radioactive carbon and beryllium in tree rings, scientists ruled out a bunch of other possibilities. At first, they considered that it was a smash-up between neutron stars or a neutron star and a black hole. These types of crashes produce a super quick blast of gamma rays without any light show, which lines up best with the evidence. But these kinds of collisions are super rare. Plait thinks it's kinda unlikely that this is the answer. He figures we should only see one of these events in our galaxy about once every million years. So having one just 1,200 years ago seems pretty wild. Scientists are seriously worried about these rare events. If one happened closer to Earth, it could seriously mess up life on our planet. Even if it was thousands of light years away, a similar event today could cause chaos with all the fancy electronic systems we've come to rely on. So it's a good thing those gamma ray bursts are so rare, because if they were more common, Earth might be in for a rough ride. You may think that if our planet could withstand mega radiation blasts, it can easily withstand something less frightening. Let's say grasshoppers. Sorry to say that, but it's not exactly true. Back in 1874, during a hot summer in Kansas, things took a strange turn. Grasshoppers, or should I say locusts, invaded the Great Plains like nobody's business. They came down like a storm, blanketing houses, trees, and even poor trains passing by. These bugs were on a mission to cause chaos. Farmers had to scramble to protect their wells and just about anything else worth saving. Locusts landed everywhere, wreaking havoc on everything in sight. Even poor sheep lost their wool. Locusts even stripped paint off wagons and handles off pitchforks. This is how destructive they were. Livestock tried to fight back by eating them, but there were just too many of these insects. That year, those critters caused about $200 million in crop damage. The locust invasion was so tough, even the US Army stepped in to help. In the end, locusts began to disappear, sparing the plains from further devastation. Natural disasters can be even more unexpected than radiation blasts from space and locust invasions. Check this out. Back in June 2017, a reindeer herder up in northwest Siberia was minding their own business when they suddenly heard a crazy loud blast and saw smoke shooting up from the ground. If that happened to me, I'd need to change my pants. Sorry. Later on, they found this huge hole that was like 23 feet wide and nearly 65 feet deep and was surrounded by chunks of ice and dirt. It turned out that there were over 17 such black holes in the area. They were filled with peaty water and shrouded in mystery. Some folks thought those were sinkholes. Others were sure they were left by top-secret device tests or even a bunch of meteorites. Now, the latest idea is that these holes are actually craters caused by the Arctic warming up and melting the frozen ground. The theory states that as the ground thaws, gas pockets trapped beneath the surface burst through, creating such dramatic holes. Apparently, these eerie craters have been showing up in specific spots in Siberia where ancient geological faults have been leaking out hot natural gas for ages. Combine that with some leftover methane from old lake sediments, and you've got a recipe for some explosive surprises as the planet heats up. Not scared yet? Alright, maybe you're afraid of darkness, huh? If so, you wouldn't like it back in 536. It's the year when the world went through a crazy 18-month period of darkness. A mysterious fog covered Europe, the Middle East, and parts of Asia, blocking out the sun and causing chaos. It was like the Dark Ages, but for real. It turns out that the main culprit behind this fog was a volcanic eruption in Iceland. This eruption spread ash across the northern hemisphere, causing temperatures to drop and crops to fail. People were freezing and starving. It was a mess. Historians from back in the day even talked about how weird it was. The sun looked like the moon, summers were freezing cold, and even China had summer snow. It was all because of the volcanic ash blocking out the sun. And to make things even worse, this period of darkness sparked the beginning of the bubonic plague in 541. Talk about a rough time to be alive. Let's go back to Siberia real quick. Back in 1908, way out in the wilds of Siberia, an asteroid dropped for an unexpected visit. Today, we know it as the Tunguska asteroid, but it didn't get its name instantly. Local folks only caught a glimpse of the show. A bright fireball streaking across the sky, followed by a massive boom. Trees went flying, fires blazed, and animals weren't too happy about it either. But since the area was so remote, not many folks took notice. For almost 2 decades, nobody bothered to check out the Tunguska site. People had too much on their plates back then. But then, scientists finally made it out there and found evidence of the asteroid's shenanigans. Later in expeditions, they found some spacey microparticles. Fast forward to now, and NASA has a whole planetary defense thing going on. They even sent a mission to test out asteroid deflecting tech. Because who knows when the next cosmic rock will come knocking on our door, right? In the middle of the 19th century, there was one more epic solar storm called the Carrington Event. It may not sound like a big deal to you, but it had pretty rough consequences. The next day after the storm, Earth was hit with this insane geomagnetic storm that threw telegraphs off the rails and brought auroras to the tropics. And it's the place where they normally never show up. Turns out, all this space weather madness started with weird stuff happening on the sun's surface, like sunspots. From these spots, solar flares and other crazy electromagnetic stuff can pop out and mess with our technology. Massive solar storms like this one can shoot out from the sun at speeds of up to 1,800 miles per second. They can contain billions of tons of solar material, complete with a sassy little magnetic field that loves to mess with Earth's magnetic field when they meet. Now, listen closely. We're getting close to the next solar maximum in 2025, so it's a good time to check out the history of the worst solar storms, like the Carrington Event, and take notice. Imagine if a similar storm hit today. An internet apocalypse, anyone? Businesses would be sent offline and we'd be facing some serious damages. Luckily, these mega solar storms don't happen very often. But hey, space weather is tricky to predict, so who knows when the next one will hit?